guys can probably guess from the title, I've got my work cut out for me. Oh, is this one on too? No, we're good? Maybe I'll turn that one off. Okay. So today we're going to be talking about a subject that some of you have probably heard a fair bit about. So we've been in the middle of a pandemic. We have been dealing with the fact that when microorganisms and other things spread around the world, they change the way that we live our lives. Well, the same has happened with honeybees. There have been these changes forced in the ways that they interact with the world because they have to, in some ways, isolate from each other for different issues that they have as a result of infections and viruses. And as we are better able to understand what's going on with these pandemics, we can do a lot better of a job of stopping them. Imagine if when our pandemic surfaced, the most recent COVID-19 pandemic, when that issue first surfaced in China, if we had started studying it, or if we had started studying even prior to it becoming such a large issue, we would have had the tools necessary to stop this at its start. And I want us to do something similar with the issues that we are seeing right now with the Tropilaelaps mite. So, before we get into this, I think there's a really important question that we don't ask enough. People are very quick to get really frightened about the circumstances that we have in honeybee colonies, where it seems like every few years there's a new weird issue going on. But the question that we need to be asking is, why are there so many creatures, so many microorganisms, so many large organisms that want to get into honeybee colonies and live there? And it's because, honestly, guys, a bee colony is one of the best places to live. If you can get in there, you've got guaranteed food for the rest of your life. The temperature and humidity is constantly regulated. There's even a mass transit system if you're small enough to ride around on the bees. As a matter of fact, there is a round-the-clock security detail that is willing to use lethal force, typically lethal against themselves, but still lethal force to protect that colony. If you can get into a honeybee colony, you have everything that you need and you are incredibly well protected. And something that might allow you to connect a few dots here. Whenever I give presentations about varroa mites, about Tropilaelaps, people ask me every time, invariably, it probably would have come up in Q&A today if I wasn't saying this now, why don't we just release something into the colony that eats the varroa mites? Then we've solved the problem. Boom, mic drop. And I love that way of thinking because I got my start working with biological control, finding the thing that controls the creature in their native range, bringing it here, fixing the problem. Varroa doesn't have a natural enemy that we can release into the colony to kill it. Do you know why? Because they live with honeybees that protect everything in that colony, including the things that are trying to kill them. And as a result of that, even though there are some generalist predators like pseudoscorpions and predatory mites that will attack varroa, they'll attack them on the bottom boards, they'll attack them in debris, but the bees are not going to allow those creatures to climb up into the rest of the colony and just pull them off of the brood and things. The bees will defend that with their lives, and unfortunately, they are protecting their parasites. So a honeybee's nest is this fortress. And if you can figure out how to get in, you have access to one of the greatest food sources out there. So let's see. Yeah, it'll only show on one screen. This will be interesting for laser pointing, but I guess I'll just rotate between them so that I'm being fair to the entire room. So varroa, we know, go after the brood specifically in intention to obtain fat body and the nutrients that are in fat body. It's something that's very important for their reproductive processes. They have this incredible resource available to them because every single larva, pupa inside of these colonies is a sack of amazing nutrients. Because as they start developing into an adult bee, as they transition from being a larva, this defenseless, legless, wingless, eyeless blob, and they start transitioning into being a pupa, there are enzymes that go throughout their body and break down much of what their body was so it can be structured into what they will become. So those honeybees are sitting there with a pretty much fully digested body, and creatures that want to feed on them don't even have to work very hard in different digestive processes because their prey has been breaking itself down and has turned itself into this delicious soup. So it's a great place to be for these organisms, and it shouldn't surprise us that so many weird creatures like these mysterious mites have made their way into honeybee colonies. The video that you're looking at right now, captured by a USDA researcher, Lilia de Guzman, this is not sped up. Those weird little objects that you see darting around the comb, those are Tropilaelaps mites. To magnify it for you, that is Tropilaelaps mercedisi, a very, very weird little parasite. In some ways, elements of its behaviors will be familiar to you from what you understand about Varroa, but then there's a lot about it that simply isn't. So just as an introduction to this parasite, there are 4 species of Tropilaelaps mites, and you'll hear me say tropy mites from here on out because Tropilaelaps is a mouthful, and I have watched people struggle endlessly to say it back to me, and this is an organism that has seen so little study that it didn't even have a common name. And so I decided to give it one, and it really caught on, and people have been calling it the tropy mite, so I'm going to stick with it. So these tropy mites, there are 4 different species: Tropilaelaps clarii, Tropilaelaps mercedisi, Tropilaelaps coenigerum, and Tropilaelaps taai. The only ones that we really focus on right now are the 2 that you see in red. These are the 2 species that have successfully transitioned from their original host, which is the giant honeybee, Apis dorsata, to a much smaller honeybee, Apis mellifera. And this is a very recent transition, a transition as of just decades. And the concern there, evolutionarily, is that they have not had time to achieve a balanced relationship with the bees. And so they kill their host very quickly. When we think about parasites, we think about organisms oftentimes that are very detrimental to us. When you typically don't think of a parasite and think, oh, that's something that's living in me and is happy to have me as a home. You think, no, this is a monster that is trying to destroy me. But that is the wrong way to think about parasites. Because honestly, a parasite doesn't want to kill you for the same reason that you don't want to burn your house down. All of your stuff is there. You live there. It keeps you going. Parasites don't want to kill their host. Oftentimes, when you see a circumstance where the parasite is constantly killing its host, and that is the norm, that's a circumstance where there is not yet a balanced host-parasite relationship. What keeps that in balance is this fight back and forth between the parasite and the host's different defenses and attacks. And unfortunately, Apis mellifera has not achieved methods of attacking this parasite that allow for balance to occur. And so the parasite often ends up destroying the colony and would normally destroy itself if not for us. So something that happens in the natural world, if you destroy your home, you're probably not going to make it. You have made a foolish choice, and evolution is going to let you know that. We have intervened in this system. Under most circumstances, honeybee colonies separate themselves. When they are doing their little honeybee democracy situation where they're looking around for a new place to live, one of the criteria for making sure that they have found a good place is making sure they find a location that is not near other honeybee colonies. They want to make sure that it is, at the very least, the maximum distance that bees will typically drift, so that they don't have to worry about bees whose parasites have killed a colony drifting over to theirs. Now, what have we done? We've set up apiaries where any parasite that kills a colony is rewarded for it because there's a colony right next to it. There's always a new home. So we've gotten rid of the system that typically excludes highly virulent organisms from being able to consistently reproduce in these contexts. When we think about why there are not just a lot of parasites in honeybee colonies, but extremely problematic, virulent ones, we do have ourselves to thank in this process, which is probably not the most popular message for me to bring today, so I'm going to keep moving. Now, the tropy mite has a geographic range that, if you look at this map, may seem a little bit familiar to you, because it started out in Southeast Asia, so this region of the world here, Thailand, Cambodia, Laos, the Malay Archipelago, that region of the world is where these parasites started out, and they weren't found in a lot of different places. Pretty exclusive location in the tropics. And then they started expanding their geographic range. And this map is important for how we understand these organisms, because this map was the only one available for the geographic range of the tropy mites for, years and years and years. I was seeing this map everywhere, and it was driving me crazy because I gave a presentation once at EAS, and this was the only map I could find, so I used this map, and I set off a panic. There were a bunch of people from New Zealand who were here, and they were like, the tropy mites are in Tasmania? Why didn't the Australian government tell us what's going on here? I was like, oh, calm down, I don't know, but I'll find out. Turns out that was a misidentification of a pollen mite in Tasmania, and that's the reason why that section of the map is lit up as having tropy mites, but they have not been detected in that region of the world, and we've desperately needed to update these maps. In addition to that, there was one supposedly in Kenya, also a misidentification. But so since then, I've updated the map. You can find this both on the Ramsey Research Foundation website, and I will be coming out with a publication soon that will have this in it. But the interesting thing here is that these parasites have spread outside of Southeast Asia into China, into regions of the world where we did not expect them to go. One of the first papers that I read about the tropy mites, the title of the paper specifically said, Tropilaelaps, not a problem outside of the tropics, or it won't be a problem outside of the tropics. I'm like, oh, well, that's encouraging. Except they're already a problem outside of the tropics. I was reading a paper from decades and decades ago, and when you read these things in your own time, it can seem a bit funny to look at just how confident we were in certain things just a few decades ago. We're very confident in this because it seemed like the tropy mites had no capacity to exist apart from brood. So any region of the world where brood is not reared year-round, we thought that the mites could not reach those areas of the world. And then they reached the coldest reaches of China and of Korea, and we realized that we were very wrong. These parasites have continued to expand their geographic range and have recently reached the Middle East. Now that they're in Iran, I'm very concerned that they will soon be in the West. And so I've been sounding the alarm and trying to get as many people as possible to not just know the name of this creature, but to know that we don't know nearly enough about it. When Varroa destructor first started its spread geographically, so it started out in Southeast Asia, moved into China, moved into Korea, and then into the Middle East, and from the Middle East into Europe, and that's when things got wackadoodle. When it reached the West, it was able to spread into the rest of the world very, very rapidly. We found ours in the US not long after. So we are on that cusp right now where we have the chance to really think about how we can avoid the same issues that we dealt with in the COVID-19 pandemic with our bees. Our bees are already in the middle of their own pandemic. Varroa destructor is present in nearly every single colony in the US. And around the world, they are a consistent issue. There was just one continent that did not yet have Varroa, at least when I first started giving these talks, and when this geographic range map was made, Australia was the only place. And that is not the case anymore. Varroa has reached Australia. I was actually in New Zealand when they reached Australia, and so all the panic was palpable. And it's a real issue. Well, we were not ready for it when it got here. And that's one of the reasons why the actions that we took at those times simply did not stop this problem. Varroa was able to spread around the US and cause dramatic losses. And the thing that really sticks in my mind is that Varroa and tropy mites share a feature that allows them to spread very rapidly and very, very easily. Essentially, it just takes one mite to start an infestation. Why is that the case? Anytime a female mite is emerging from under the cell capping, she is already pregnant. She is able to store the genetic material of these males the same way that a queen honeybee is able to. There are some elements of their biology that are very similar there. And that capacity to store the sperm of the males that she's mated with allows her to never have to mate again. They mate under the cell capping, and from that point forward, if they go anywhere, they have the capacity to lay eggs and start a family. And people on Reunion Island were acutely aware of this because it is possible that the entirety of their infestation of Varroa started with a single mite. And it was very recent, actually, that this situation occurred, but they had no Varroa on their island. They consistently told people not to import bees and queens and everything from the mainland. Some people didn't listen, and they ended up with Varroa. And I want you to just take a moment and look at just how much the mites' populations was able to boom in just 4.5 months. They were found in just a few colonies on the island, and then pretty much all of the colonies on the island. Their loss rate went from less than 1% to above 60% in a single year. That's what happens when a population of bees that are fully naive to a specific parasite is immediately faced with this challenge. So let's talk a little bit about the tropy mites. Then I want to talk to you about the work that I was able to conduct with the help of viewers like you. In addition to funding from Project Apis M and High Flow. So check this out. These tropy mites, I don't know how many of you, when you go looking for mites in your colonies and you do a sugar shake or an alcohol wash, and then you can just look at the plate that you've shaken all these mites onto and you can just see them, right? Some of you. A few people have told me that Varroa can't be seen with the naked eye. They're invisible, and I always tell them, please put on your glasses before you go. Mm-hmm. My dad recently became a beekeeper. He's 70 years old right now, and he laughs at me because he brought in this plate, and he's like, oh, Sammy, my colonies have 0 mites, and I'm just watching Varroa walking around on this plate. I had to tell him, Dad, you have to wear your glasses. These things are so tiny. They are not invisible to the naked eye, but they're only about 1.5 millimeters in width. They're tiny organisms. Well, the tropy mites are 1/3 that size. So they are definitely on the margins of what we are capable of seeing with the unassisted eye. The structuring of their bodies, I should also point out, is one of the things that makes them really remarkably different from Varroa, and that Varroa have this giant shield on their back that they drag along with them everywhere that they go, slows them down quite dramatically. Tropy mites, not so much. Their legs are distributed around their body in a way that makes them very, very fast, so they're difficult to capture, and they're very difficult for the bees to actually catch. And that's an annoying thing for them because you will see in a colony that has a lot of tropy mites in it, one of the key features that you'll see there is that the vast majority of the cells are just uncapped. The bees are running around trying to uncap everything because the mites are just shooting out of these cells, and as soon as they uncap it, the mite just escapes from them, and it seems to confuse the bees, and they just start uncapping everything. It's a bit of a mess to watch. In addition to that, the tropy mites are not polite dinner guests, I would say. Oddly enough, Varroa is pretty polite. When they choose to eat, you know, they set the table, they wipe their mouths, they're good guests to have. Insofar as when they feed on their host, they bite a single hole into the body of their host, and everybody, all of the mites, congregate around that and feed through that hole. That minimizes the damage that's caused to the host. Even though Varroa and honeybees haven't achieved a fully balanced host-parasite relationship, they've been together longer. They've had a chance to figure each other out for much longer than the tropy mites. When Tropilaelaps mites feed, all of those spots that you see there are different feeding holes over the course of just a few hours. These parasites bite a new hole every time that they feed. They don't turn blue naturally. This is a vital stain that we used to visualize where they're feeding. But this is really problematic for the bees because each of those sections, it forms something that's analogous to scar tissue. That region of the bee's body, whatever it's destined to be, then becomes immobile as it's caked over with that scar tissue. And so if that was destined to be a leg, you've got bees walking around with legs that they can't bend at the joints, and even without viruses can cause deformities. And you can see it here on the antenna of a bee that was fed on a region that would become the antenna. And then viruses. They also spread viruses. We have confirmed that deformed wing virus, acute bee paralysis virus, both of which can be spread by Varroa, can also be spread by the tropy mite. Black queen cell virus has also been detected in a single study to this point. And you might be thinking, all right, well, that's still fewer than Varroa. Varroa directly vector at least 5 viruses, and there's about 13 others that are associated with them in one way or another. Don't take a deep breath or a sigh of relief just yet, because we haven't tested any of the other viruses. And I have a very strong feeling that as more research is conducted and people test these viruses, we will find that these parasites are capable of transmitting those as well, or at least some of them. And finally, as we think through what we know about these parasites, well, you guys might be a little bit surprised that I've gone through 4 slides now, and I've detailed the vast majority of what we know about the tropy mites. It's kind of sad, it's rather upsetting, but very little work has been conducted about these organisms. And as I look through the literature and also talk to researchers and some individuals in different governments, as we talk about these creatures, what we typically hear is they have not yet reached parts of the world with the large economies necessary for them to become a priority in study. They are in the developing world at this point. Now, sit down, let me rap with you for a second. Does anybody see an issue with that way of thinking? Anybody? Yes, maybe, a little bit. So we have this is not my problem yet sort of way of thinking about the world when things are happening in other people's borders. However, we've globalized our world. We now have a global ecosystem. The discrete ecosystems that once existed will no longer allow us to think about the world as that's their problem, these are our problems. When something becomes a huge issue overseas, some sort of communicable illness or disease, we should be ready to study it immediately. If we have the capacity to, if we know that something can become an issue, we should study it then before it's even reared its ugly head, because then we will know how to manage it when it arrives. And in addition to that, those are the selfish reasons. If we want to be selfless about it, helping people who don't look like us is its own reward too. There are people right now dealing with ridiculous losses as a result of this parasite, and their lives matter no less than ours. I mean, I'm just getting a little preachy. My dad's a preacher. These things happen. But let me also say, when these parasites arrived in Pakistan, 3 decades ago? Almost 4 decades ago. When these parasites arrived in Pakistan, things got really weird. They lost 100% of their honeybee colonies in less than a decade to this parasite. All of them. We have ignored it, knowing that it has the capacity to do that kind of damage. So, they actually had to replace all of their honeybees they sent to Australia and got a whole new shipment of bees sent over. But yeah, that's what we're working with. So, what do we know about this parasite? We know enough to know that we don't know enough yet. And we have to really get on that. Because the populations of these parasites grow very, very rapidly within the colony as a result of one element of their life cycle that's really interesting to me. They don't need to spend time on the adult bee population in order to continue their life cycle. And we're finding that Varroa needs at least between 3 and 13 days. It needs to spend that time on adult bees feeding on them. I've got some work that I just submitted that details the reproductive system of Varroa, the connections between the reproductive system of Varroa and the fat body of bees. There's a set of nutrients that's different in the adult bees, the adult bee fat body, and in the brood fat body. And they need both in order to create their egg yolks and actually produce viable eggs. Tropy mites don't seem to need that. They can just feed on the brood. So what does that do? That means that they don't need a 2-week reprieve between each reproductive cycle. They can jump right back into the cells and start reproducing again. So their populations grow, and this is an estimate at this point, but between 2 and 3 times faster than the Varroa populations, and that allows them to overwhelm colonies much more quickly than Varroa mites can. So, you've seen the things that we know about this parasite. Here are some questions that I've been proposing that we need to answer most quickly about these organisms, and then I'll take you to the really fun part of this presentation, the part where after raising money and applying for grants and starting the Ramsey Research Foundation, I was able to go over to Thailand and answer some of these questions. But let's jump in. So what do these parasites eat? That is the million-dollar question. Because when I first got to Thailand, I remember talking to some researchers. So I was there actually to study Varroa at the time. I didn't even really know that the tropy mites were a big issue. And I was there to study Varroa, but I remember someone saying, oh yeah, and these their word for it, so topi. These mites are feeding on the hemolymph of the bees. I was like, oh, that's exciting. It's really cool that you guys actually did experiments to determine that. And they're like, oh no, we didn't have to do experiments to determine that because tropy mites and Varroa mites are very similar, and Varroa mites feed on the blood of the bees. I was like, oh buddy, have I got a story for you. So we found out that that was not the case. And if it's not the case for Varroa, that calls into question whether it's the case for the tropy mites. So are they feeding on the fat body? Are they feeding on the bee's blood, the hemolymph? Are they feeding on some other tissue entirely? We don't know the answer to that. In addition to all of that, we need to know if they are feeding on the adult bee population, because they can be found on adult bees, very briefly. But what are they doing when they're there? Because it doesn't seem to be their primary mode of spreading between colonies for them to ride on the adult bees. And so if they don't have any good reason to be on them, what are they doing? It has been assumed that they don't feed on the adult bees, and there are very good reasons to believe that, but we need to prove it. What does it take to actually rear these parasites in the lab? A lot of the studies that we would want to conduct on these organisms will require us to really observe them under very controlled circumstances. If we can potentially rear them in the lab, we can get a lot of work done. But we don't know how to do that yet. And how do they spread between colonies? Knowing exactly how these mites are getting from one location to the next, from country to country and from colony to colony, is very important for us being able to mitigate that spread should they ever arrive on our shores. And what does it take to control them? How do we kill these parasites effectively without killing the bees that they live with? Is formic acid an effective resource? Amitraz, can we use heat treatments? Are brood breaks going to be the most effective method of controlling this parasite? We need to know the answers to those questions, and none of those questions were answered at the time that we started this work. And then, just to be really nerdy, I really wanted to know more about the life cycle of this organism, because much of its life cycle was assumed from Varroa. And there are a lot of differences between these parasites. We need to know more. Well, one of the reasons why it's difficult to actually observe the life cycle is because it occurs under the cell capping, in these opaque, totally darkened cells. And the ability to see what's happening there is very difficult to achieve. So for Varroa, we've been able to kind of figure out what's going on under the cell capping by doing a stop-motion system of uncapping the cells after a specific amount of time and seeing what the mites are doing in that very moment. But the second you open that cell, that is the end of the data that you can collect about that mite, because the influx of air into that cell lets them know the jig is up. They stop conducting all the behaviors that they were before that, and you get just a glimpse into what was occurring in that cell. It is like someone walking past a window. You can see them when they're in their field of view, but you don't know exactly what was happening before, and you don't know what will be happening after. And so to actually be able to visualize this, to see what's happening under the cell capping, would be the holy grail of understanding these parasites. And then, how do these mites interact with each other? Because the earliest research that I've seen about them says that Varroa and Tropi mites will not exist in the same colonies. They just rapidly outcompete one another, and one of them dies off. Typically, the Varroa mite is outcompeted. And that doesn't seem to be the case. I have found Varroa and Tropi living happily side by side in these colonies, and I wanted to know what the impact is on the bees themselves. Are they competing with each other in this process? Or are they cooperating? Do they synergize and somehow become worse than the sum of simply their parts? Can both of these parasites reproduce on the same host? The literature says no. I've seen some things. And some stuff. And then how is the host impacted by this? All right, guys, let's jump in. Data, woo! Okay, so you are now looking at the very first video ever captured of a Tropilaelaps mite inside of a sealed brood cell on a honeybee host. Now, you might be thinking, how did you get a camera inside of a tiny little brood cell? Well, I don't really like keeping secrets in science. I think that we should all have access to this kind of stuff, so I'll tell you all about it. But I found this to be really exciting that we could actually do this. I've replaced two of the walls of the cell with this high optical clarity glass that allows for us to actually see what's happening inside of these cells without ever opening it. And so because the study that we're trying to conduct here has been bifurcated into two segments, one of them, we are trying to actually see the life cycle of these parasites, and so we've been referring to it as the Cite the Mite study. And the second, we are trying to murder these parasites. We have referred to it as the Fight the Mite study. So let's start with Cite the Mite, and we'll move down to Fight the Mite. Uh-oh, do videos work here? Haha, okay. So, honeybees have been locked in this mortal struggle with their parasites for some time now. And you are seeing what it actually looks like as all of this occurs. That blob that you see there very close up, there's a lot of detail that I want you guys to really see here, because all of that white goo is fat body tissue. And you can see the Varroa mite has its mouth parts sticking straight through the exoskeleton of that developing bee, right into a blob of fat body. And we've been able to learn a fair bit about Varroa. Over our time studying these organisms, we've known that they weaken the immune system of the bees, that they transmit viruses, they are able to reduce the metabolic activity of the bees themselves, but really the biggest thing that all of this leads to is premature death of these hosts. But it's the Tropi mites for which a lot of these things are still very mysterious. Now, Tropi mites and Varroa mites do enter the same brood cells sometimes. And it's been interesting to see what exactly happens while they're in there. And as they're running around inside of these brood cells, I am capturing all of these behaviors and then taking notes in a behavioral analysis software so that all of this behavior can be analyzed, because there's too many question marks here. For Varroa, there's a lot more about it that we actually understand. So actually getting these close-ups, seeing how they feed, where they feed, what they're doing, how they interact with their offspring, all of it is just, I'm enjoying getting to do this work. But the mites are under the cell capping for close to, for more than a week and a half-ish. And that is a long time to be watching a single video. The recording software that we have going runs for the entirety of that period. that 11 to 12 day period that they are under the cell capping with these bees. And it's a lot of data. Just a single mite with the bee video is, 12 days long, and then I have to watch it sometimes at slowed down speeds so that I can get all the different behaviors. So if you're asking, like, when is this going to be published? Give me a sec. The great thing now is I'm a professor and I have grad students. So, woo! So grad students are amazing because they have the capacity to really help with a lot of these different projects. But this one is my baby, and I really want to see it done very well, so it's going to be tough to hand all of it over. I'm working on that now, figuring out how best to delegate. But in order to actually conduct this work, we started out using these tubes. There we go. These tubes made of very high optical clarity glass, and taking compressed beeswax and smushing the two of them together to create this system where two of the walls of the cell, the typical 6 walls, the hexagon, 2 of the walls have been removed. This allows us to see straight through to what's happening in there, and then we recap the cell. Actually, we've been taking cappings from other cells when I do this artificially, but you can actually push these artificial cells into a regular frame, put it into the colony and allow the bees to cap it themselves. That takes a long time when you're trying to do that and then only going for the ones that actually have a mite that has naturally infested it. So that can take a bit, but it allows us to really look at precisely what's going on in there. But then we needed to figure out how to view all of this without disrupting the behavior of the mites. If you take it out of the colony, the change in temperature, the change in humidity can disrupt the behaviors naturally occurring in the mites. So we then cut a hole in an incubator. Don't worry, it was an incubator that nobody wanted. We cut a hole in the incubator, set a microscope on top of it. This is with one of my friends who he has a machine shop in his garage, and after church we would just sit around and work on this for hours and hours, and it actually turned out it worked pretty well. We put this microscope on top of it and then stuck a camera on top of the microscope, and we're able to film these behaviors. When we actually got funding through viewers like you, we were able to actually buy a more robust system. And so you're seeing the relay recorder here that was the game changer in all of this. Because prior to that, every 12 hours, every 8 hours, I had to show up and change the little cartridge in there so that we could record more data, download the data onto my computer, and then slip the cartridge back in. We're losing time. It was taking up a huge amount of resources. This relay recorder can record for up to 14 days without stopping, and it's amazing. It was a game changer for us. And it's allowed us to actually visualize all of these different behaviors in the mites. We've noticed this interesting antennating behavior, like right before they feed, they drum on the body of the host. They don't have antenna, but their front legs kind of behave like them. And so they tap, 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 and they move a little bit, and they tap, 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 and then they find the section where they want to feed. Their front legs have taste and smell sensors on them and allow them to actually determine whether what they are tapping is a good source of food. But something else that we also found really odd. Does everybody see the mite, the varroa mite here? So that mite, every time the varroa mites go into these cells, they flip upside down onto their backs and just stop moving in the brood food. Why they're doing this, we don't really know, but I got this crazy idea to stop them from doing it. So I actually stopped them from going down into the brood food, like got a probe, knocked them out of the brood food. They continue being alive after that. They're fine. They continue on, but they don't produce, they don't go into their reproductive cycle for some reason. So there is a necessity for them to go in the cell, climb under the body of the larva, and hang out in the brood food for several hours. And we don't know what they're doing. They look dead. They hardly respond to any stimuli whatsoever while they're in this phase. Not the only researcher to observe this by far, but we don't know what's happening here. We also know that that doesn't happen with the tropimites. If you watch this video that you're seeing here, this little snippet, you'll see that there's a tropimite running around in the background here. It's immediately able to jump into the cell and start feeding on the bee itself, while the varroa have to spend close to 10 hours just doing absolutely, well, what seems like nothing. So we're very interested in what's going on here and the difference between these two parasites and their behavior here. But something else that was also really fascinating is this cocoon spinning phase that I've always wondered, why do they even bother? This is one of the most paltry cocoons I've ever seen in my life. So few fibers are involved in the actual cocoons. They spin around themselves, and it tends not to be like the cocoons that you see for a caterpillar turning into a butterfly. But you'll notice that the varroa mite climbs onto the body of the bee, so it was in that dormant phase. It jumps onto the body of the bee during the cocoon spinning phase, and if it does not do this, it dies. So when they are spinning their cocoon, they move all around the cell. They touch pretty much every surface, and if they touch a mite that's on the wall of the cell, they immediately start banding silk around its body to stick it to the wall or stick it to the floor of the cell, and it's amazing to watch. It's really, really, really cool. I was trying to download one of the videos this morning, but these big 4K videos take a long time to download, and I couldn't get it into the presentation in time. So I won't be able to actually show them nailing these mites to the floor of the cell, but the silk, even just a few fibers of silk over the mite's body, makes it very hard for them to get up. It gives them enough time to actually get the mite stuck to the bottom of the cell altogether. And so, yeah, lots of cool stuff that we get to find in here. Unfortunately, that doesn't happen with tropy mites because they don't go into that dormant phase, and they just run from the bees because they're much faster. So they're able to run away from this cocoon spinning phase and actually keep themselves safe in the process. So we take all of these behaviors, we compile them into a pie chart, basically, and it'll show us all the different things that the mites are doing over the course of their time in the cells. But then after all of that is the Fight the Mite initiative, where we've really wanted to know. I wanted to make sure that I'm not just providing you guys water cooler facts that you can tell your friends about, oh, wow, this is really weird that the mites do this and they do that. I want you to know how to kill them. So the Fight the Mite segment of this study was one that required me to think on the level of the mites themselves. Multiple countries have had to deal with these mites at this point. To understand why the mites are still able to consistently thwart these bees and these beekeepers, we have to understand the differences between the life cycle of the varroa mite and the tropy mites. Because you might be thinking, why don't we just take the treatments that we already have for varroa and adapt them to the tropy mites? Makes perfect sense. A lot of people have tried. Very rarely has it worked. Specifically, I think it's related to their life cycle. The vast majority of treatments that we have for varroa target the period of time where the varroa mites are on the adult bees. The cell capping is it is this waxy thing that unfortunately repels the vast majority of pesticides that we have available to us. They can't get through that capping to the mites when they're in their reproductive phase, so it makes perfect sense that we target the period of time that they're on the adult bees. But we cannot do that with tropy mites. Those treatments have been adapted for tropy and have failed consistently. One of the biggest failures was in amitraz, which was tested in China. Really thought like this could work because it works so well on varroa. Did almost nothing. And the worst part about it now is that the mites, having been exposed to that amitraz, have developed resistance to the chemical itself. So even if we found a way to deliver it under the capping, still wouldn't kill the mites. So we have to find a way to expose them to something that is going to focus on the period of time where they are invading cells or when they are under the capped cell. So during my time in Thailand, this is actually really fun. In different locations in Thailand, we placed 20 honeybee colonies and spent our time with these colonies trying to figure out how to actually kill the mites. So 20 at each location, 3 locations, 60 colonies. That was one of the locations in northern Thailand. And if you're wondering how we moved around so many colonies at once, I was wondering how we were going to do it too, because you've seen these noodly arms that I've got here. I wasn't sure what exactly was going to happen. And then the guys just showed up with this amazing counterbalance that one of them had built from some scraps, and I was like, you know what? Y'all are all right with me. They say it's tough to find good help these days, not in Thailand. Not in Thailand. So the colonies were strategically placed in locations where at best the colonies were going to have a substantial amount of forage and a good source of water that is naturally available to them. And so several of them were placed in these forested areas, typically around longan and lychee trees, which repeatedly produce blooms that are able to feed these bees. And then every single frame and every single one of these colonies was labeled so that we could track the progression of different issues like disease or see how the food is actually, how that is potentially being affected by different treatments. And so as we were preparing these colonies for treatment, I noticed something that I didn't think about before I went to Thailand the first time to conduct this study. So the first time that I went to Thailand to study these parasites, so when I was specifically focusing on tropimites, it was at the very end of 2019. Any guesses as to what happened to that project? I was a casualty of the pandemic. It was really rough, guys. I bought all of these colonies, purchased 60 colonies for this study, and then out of nowhere, COVID-19 hits like only less than a month into my study. And I thought, okay, 5 weeks to flatten the curve. I'll go home, I'll come back, everything will be fine. No. So within about a month and a half, almost 2 months of me leaving, giant hornets had cleaned out 48 of my 60 colonies. And so I had to buy them all again when I got back, and that was fun. But I learned a few things in what I've been thinking of as the practice run of the study. One of the things is that the fronts of these colonies are structured in a way where they will not allow the hornets inside. There are these two very, very, very small entrances that are about the width of 3 bees and about the height of a single bee, and you can't get anything else in there. And I wanted to test out these commercial heating pads, so we actually had to break open the fronts of these colonies, which is one of the reasons why the hornets were able to get inside. I've since learned to replace the front entrance after we finished that part. And so we wanted to test a few different options. I wanted to make sure that you guys, that not just you guys, but anyone else who ends up facing a tropimite issue has multiple resources available to them, not just one chemical. When I've looked at the literature, what constantly happens is we find one chemical that works, we use it to death until resistance arises, and then we search for another chemical. And oftentimes, it takes a long time before we have multiple ones that work that we can rotate between. And so I wanted us to start with a treatment option that is chemical and then a non-chemical treatment option and see what we can do here. Formic Pro was what I thought of immediately because of its capacity to actually penetrate the cell cappings and go after the mites that are there. And so these are colonies that have been exposed to Formic Pro. And you can see the bees are, they're chilling. They don't want to be anywhere near the chemical, so they're not moving around close to the top of the colony, but you know, they're fine. They're going in and out. They're living their best lives. And then I wanted to understand how the beekeepers in Southeast Asia have been managing this parasite because they still have colonies. They're doing something. The key feature that they're using is brood breaks. They are constantly breaking the brood cycle. I asked some beekeepers, why are the colonies all one box, and why do they tend to have so little brood? And eventually, over time, they got comfortable enough with me to start letting me into the ways of the world there, and they do not like brood. They want to get rid of brood as much as they can because the very short sentence that they provided me in Thai translates to brood means death, or lots of brood means death. A colony with a ton of brood may seem to you like a great colony to have. In Southeast Asia, that is a colony that is likely going to die very soon because the more brood it has, the more opportunities there are for tropimites to feed and to reproduce. And so they constantly break the brood cycle. Every time that colony broods up enough that it has filled that box, they take out all the brood in that colony and they let them start over. That kills the vast majority of tropimites in that colony and gives the colony the chance to continue on. But if you're going to produce honey, if you want your colonies to actually be able to pollinate large swaths of plants, you need them to have a strong enough workforce to do so. And so I talked with some beekeepers and found that under those circumstances, they use liquid formic. They take these big drums of formic, they portion them out into these little trays, and then soak paint stirrers, these cool paint stirrers right here from a place called Home Depot. Yeah. And they slip those into the front of the colony that the formic then aerosolizes into the colony, knocks down the mites, and the bees are okay-ish. I want you to take a look at this. So this is me doing this. And this stuff is caustic. This is 85% concentrated formic acid. And so I'm wearing my personal protective equipment. I've got a whole mask on there. But look at the response of the bees here. Look at them. I mean, they are tripping all over themselves to get away from this stuff. They are not happy. But we don't need those bees to remain where they are for this treatment to be effective. We need the brood not to go anywhere, because those bees are carrying very little, if any, mites outside of the colony with them. It's the brood that has the mites. Commercially available heating pads have also been proposed as a means of potentially treating varroa mites, and I was very interested in whether this could work for the tropy mites themselves. Heat would be an option that can penetrate the cell capping and impact the population of mites below the cell capping. And so these heating pads, commercially available, they heat the colony to 106 degrees Fahrenheit, 41 degrees Celsius, for 160 minutes, impacting the population of mites inside of the colony. You can see these colonies here that have been treated, that are currently in the middle of a heat treatment, and you can see the response of the bees is to leave. The queen, and I've only actually checked this in 2 colonies, but in both that I checked, the queen was at the center of that mass of bees. She actually leaves the colony, hangs out on the front, and I think that that is a way of preserving sperm viability, potentially. You heat sperm up too much, and then it's no longer viable, and then you've got a queen that can't do her job. But as soon as you take the heating pad out, they go back into the colony, the temperature goes down, and a few of the bees that land on the heating pad don't make it, and it's a bit sad for them, but by comparison to the population of the entire colony, it doesn't seem to be a significant number of bees. But all of those little dots that you see on that heating pad, all of those are varroa mites, which is kind of cool. And then, this is one that I was surprised to hear about and was excited to be able to test, specifically for the fact that it could potentially reduce our carbon footprint quite substantially. Instead of us adding a chemical to the colony, instead of us having to plug in these heating pads, there's this solar-powered one that these researchers these entrepreneurs have developed. It's a solar-powered system that actually delivers heat through a heating coil in the frame to individual cells, such that instead of heating the entire colony, you have a very energy efficient system that's zapping the cells themselves with heat at about 40 degrees Celsius. 40 degrees Celsius is right at the line where the mites should start dying, but sometimes they can survive that amount of heat. And so we set up our solar panels. That was not within my wheelhouse, so thankfully some students at the university and their dad helped us out with getting the solar panels and everything set up. And for each of these studies, we conducted a frame-by-frame inspection. Oh, I am approaching my time. All right, so let's get, instead of me describing all the different things that we did, I'm going to get to the data really quickly, and then we can get into the question and answer. So we conducted a frame-by-frame inspection of the different brood frames, of all the frames in the colony, hence why we had to have that tag, that label, so that we would know exactly which frame we're looking at and could get really good data about what exactly is going on in these frames. And for our colony inspections, we also looked at just the size of the population of bees within the colony. But in order for us to also understand how the mite population is being impacted, we had to have a way of quantifying the number of mites that are found inside of the colony. Now, you guys might be thinking, that's pretty simple. That already exists as a thing. There are alcohol washes, sugar shakes. Those don't work with tropy mites. The vast majority of the mites are not going to be on the adult bee population. Typically, 1% or less of the mites in the colony are on the adult bee population. And so these, in order for us to see what's going on, we have to cap cells and see how many mites are there. So I've been conducting 100 cell inspections. It takes a good amount of time. And so we've been trying to figure out if there is a smaller number there that still provides us with accurate data as to how many mites are in the colony. But a 100 cell inspection allows us to see how many mites are present. We also looked at whether the queen was present by looking at the eggs. And all of the contents of the cells were removed. We got to see how many mites were in each cell, what stage of development they were, and recorded all of that data. And this is a representation of that data as a figure. Any of the white hexagons that you see here is just a regular old honeybee with no parasite inside of the cell. And any of the white hexagons that are replaced with the silhouette of a parasite, that is a cell in which, during our 100 cell inspection, we found parasitic mite inside. So this is the day before treatment. We sampled all of the colonies immediately before treatment. Then we sampled them a day after treatment, and then every week after that, for 8 weeks, we looked at the mites inside of that colony. So this is the colony after it's been treated, and you can see that at times we were able to achieve 100% kill of the mites inside of these colonies. This one was with heat treatment, actually. So in our 100-cell inspection, we didn't find any live mites. The ones with the red X through them have been killed. As we look at the averages and the numbers of mites present here, you'll see some pretty distinctive differences between the treatments. Now, formic acid, it did its job. When I say, so this is our starting population here. You see over on the side, so the number of mites that we have inside of cells in our 100-cell inspection. And so this week 0, what you see here is the treatment, the sampling before we actually treated the mites. And then week 1 is after we treated. And you can see this massive drop with the usage of Formic Pro and liquid Formic in this study. But then for the heat treatments, the red and orange arrows that you're seeing here, not only did we see that the drop was substantially less pronounced, but for some reason with the heat treatment, we did a single heat treatment with this one, it drops and then bounced back up. Consistently did this, and we didn't fully understand why the population seemed to rebound, but 2 weeks after treatment, the population dramatically rebounded. It then dropped again, but then sometimes rebounded immediately after that. We also saw the greatest amount of variability of any of the treatments with the heat treatment. Sometimes we would achieve close to 100% kill as the average for the treatment, and then sometimes we would achieve something closer to 15%, and we just couldn't figure out exactly what resulted in that, whether it was the equipment itself or whether the population of mites is somehow adjusting to this amount of heat. And as we look at, if we just take that data and then pull out the tropy mites themselves, because that was all of the mites, the varroa mites and the tropy mites, but if we look at just the tropy mites themselves, you'll see that formic acid is very, very, very effective from what we see here. I mean, we get 100% kill within the first week, and the population never rebounds. The solar cells were very difficult, unfortunately, to really get data for because we had to put these frames into the colony that have the heating coil into them. The bees had to build out wax onto them first. That took a long time. Then they had to start rearing brood in them, and then the mites had to finally invade the colony. And so by the time all of that occurred, the population of mites that we started with was very low. And so we can't make any clear pronouncements about the efficacy of this on the population level. We can, from the level of looking inside of these cells that have directly been impacted by this heat. And we do still find live mites consistently for the solar cell colonies. And so we've been talking with the individuals who make this product about making it just maybe 1 or 2 degrees hotter. It seems like because they're right at that 40-degree mark, that's right on the cusp of where the mites die, that is just not killing nearly enough mites. However, it did seem to be killing the eggs, and so these mites were not reproducing as much, but not taking out the mites themselves. And then when you look at the number of dead mites that we found inside of these cells, this was really interesting to me. You can also see something very clear as a trend in these studies. So the blue that you see here, these are all the mites that were alive inside of these cells. And so this is week 0. This is the preliminary week here, and you can see very few of the mites were dead when we opened up the cells. For formic acid, every single mite that we found inside of the cells was dead. For formic pro, it was really interesting, but the bees had much more of a tendency to actually remove the mites, it seems, from the cells. A lot of the cells were already cleaned out, and so we found very few mites in general, but the only mites that we found were very, very dead inside of these cells. And you found none of that in the control, no significant difference oftentimes between the heat treatment and the control for many of these, for many of the colonies in the different locations. So we separated it by location as a block design. And you can see that this continues from week to week. As you look at from week 1 to week 2, you continue to find dead mites primarily inside of the cells for formic pro and liquid formic. But after that heat treatment is conducted, there is no longer any capacity for the heat to kill the population of mites under the capping. And so that may be the reason why the rebounding is occurring. The mites are able to continue doing what they were up to again. But for formic pro and formic acid, there is a lingering effect of the formic acid in the colony. And the next time I give this presentation, I'll have all of the vapor data that we collected, but it wasn't analyzed in time. There is a lingering of that vapor within the colony that continues to be effective at suppressing mite populations for at least a few weeks. And so I am out of time, and that is why I'm glad that I'm at the end. All of that to say, we found that repeated heat treatments may disrupt some of the reproductive processes of the mites themselves, but the solar cell that we were working on just didn't seem to be consistently killing mites inside of these colonies. The application of formic acid, though, either method of applying it, so the very cheap method of applying liquid formic or the more standardized method of using formic pro, both of which were very effective at killing mites under the cell capping and achieved 100% or near 100% mortality of the mites inside of the colony. And formic pro, surprisingly, had more of a tendency to kill queens than the liquid formic. And I think it's because the liquid formic is a quick burst of formic acid and doesn't persist for quite as long, but there is this consistency of formic pro within the colonies. And in Thailand, there is never a circumstance, pretty much, where it's below 84 degrees and not very high humidity. And I think that contributed quite substantially to us losing more than a few queens in this process. And with all of that, I would like to thank all of my funding sources. This study happened in part because of viewers like you, but also because of High Flow, Manuka Doctor, and Project Apis M, all of which supported this work consistently, especially after I lost all of those colonies the first time around and needed to figure out how to replace them. Project Apis M stepped in and really provided enough funding for us to replace those colonies and get this study conducted, as well as the United States Department of Agriculture and Budapest University, who are great help in this as well. Thank you all for listening, and if there are any questions, I would love to answer them. Woo!
Looks like it works. Mm-hmm. Thank you very much, sir. Mark of Zia Queen Bees, New Mexico. Mm-hmm. I'd like to now, this time after the fact, congratulate you on achieving your doctorate. Great work.
Thank you.
Respect, man. Big respect. Okay, I'm sure you've heard this from other queen breeders. Are you seeing any resistance in feral colonies over there in Thailand that have been with us for a long time? Is there, clearly, it will be here sometime. And so, also, programs like what Sue Colby does, importing semen, I would say, well, let's import some queens that have been exposed to it, but we'll probably bring some other bugs back with us. So perhaps importing the semen might be a way to achieve some. Are there bees that are resistant at this point, and could we maybe do that to bring some, try to achieve some resistance in our queen breeding here? Thanks.
Great questions. So first of all, I whispered this a second ago, but I feel like I need to say it even louder. Don't do that. Don't bring in, please don't bring in any queens from other countries right now. And like, it's not a great idea. Even though we have very little diversity in our honeybee population in the US, that's not the way to do it. But this idea of bringing in semen from drones and having that as a way of bolstering the diversity of bees in the country could be a much more controlled measure for doing something like that without potentially bringing in all of these other issues. There are viruses that can be potentially spread in that way, and so it would be a better idea to make sure that all of that's being screened so that doesn't become a problem, but that would essentially be a part of the process. Your question of whether we are seeing resistance. Yes, we are seeing some level of resistance. Some of that resistance comes at a price. Some of the bees that we see that are surviving much longer in the face of tropy mites make substantially less brood. Their colonies grow very slowly, and in some ways that's a good thing, but I don't know that that's something that we would want to be our primary resistance measure here in the US. The bees just don't seem to have had a very long period of time to deal with this parasite, and I think as they have more time to deal with it, maybe more resistance measures will surface, especially as we start looking in other areas of the world where this parasite has been found. But right now, we're not seeing anything that looks like it's going to be the holy grail that we can breed from to create a really strong resistant stock. We are seeing resistance. We have seen, of course, resistance in Apis dorsata, the original host of these bees, and that's pretty cool. Maybe someday we can CRISPR that in, if you guys would be cool with that. A lot of people aren't down with transgenic bees.
So great talk again, Sammy.
Thank you.
So way back when I heard you last at NAPSI meeting in October, you said something there that scared the heck out of me.
Oh no, yeah, the native bees.
Yeah, have you gone back and kind of verified if indeed tropy is now spreading to other genera outside of Apis?
Thank you for asking that question. That's something that I really should make sure to include in all of my presentations, but every time I say it, I just get really bummed out. So varroa mites are actually pretty species specific. They tend to only be found in one species or a couple of species maybe of honeybees, 2 species tops. Tropy mites are the least species-specific honeybee parasite that we know of. We have found them in all 3 subgenera of bees. So we've found them in dwarf honeybees, giant honeybees, and the cavity nesting bees that we know and love, Apis mellifera, Apis cerana. What is still worse than that is that they don't seem to be specific to the genus Apis. It's not just the honeybees. They've been found in bumblebees and even solitary carpenter bees. So that's not great. The impact that they could potentially have on our native bee population is of huge concern and is something that we really need to think through, because we have 20,000 species of bees. There's more than 4,000 just here in North America. And the fact that this parasite could have a direct impact on them instead of the indirect impacts that varroa has through spreading viruses is a huge concern. One ray of hope here is that there is only a single study and a single set of researchers who have seen the tropy mites on solitary bees, like carpenter bees. That was in India. No one else has witnessed this, and so it has yet to be independently verified or reproduced. It's possible that because these parasites are very adventurous, that they may have just ended up in one of those colonies. The entire life cycle was not documented going through the carpenter bees. They were found feeding on the brood, but we don't know if they were capable of reproducing. And so maybe not, but I have not had the opportunity to verify that myself. But if there are any excitable PhD students or potential postdoc candidates in the audience who want to join the Ramsey Lab at CU Boulder, come talk to a brother. There are opportunities for you to do some really fun traveling.
Thank you so much. Great presentation.
Thank you.
With the tropy mite spending a lot of time in the brood, I was curious what you think about the potential for hygienic behavior in controlling tropy.
So the question of hygienic behavior is one that we really should be. There is the potential for hygienic behavior to be helpful to an extent. It's upsetting just how fast the tropy mites are, because as the bees uncap a cell, with Varroa, they have the capacity to actually grab the mite and end its life. We have found mites that have legs bitten off of their body, that have parts of their exoskeleton bitten into and crushed. That's great. Those are some really good hygienic bees. We never find that with tropy. And part of it is likely because they are so fast that when the bees uncap the cell, the mites realize, oh no, something's coming after me. They're able to dart out of that cell and run off and continue their life cycle. And so while uncapping the cell slows the reproductive processes, it disrupts reproduction in the mites, it doesn't lead to their death the way that it can more frequently in Varroa. And so the hygienic behavior, while it is still important and can slow the progression of the development of the population, it typically doesn't lead to the population decreasing in size. And so instead of being a resistance measure, it's more of a tolerance measure where the colony can live longer in the face of a very virulent and problematic parasite. Should I be stopping? No. I think this is the last question then? Okay.
Hi, so my question is, great presentation first and foremost. For your treatment for your Formic Pro, did you do with a single strip, or did you do 2 strips for 10 days, or did you do 10 days and then, or did you do both?
So we used the 2 strips, which I think was a mistake. I think there's just, I wanted to start off with the largest dose there, but I would not recommend that for the level of heat that we typically have in Thailand. It's a lot like Florida. So that probably wouldn't work in a set of circumstances like this. It might work in Maryland, where I'm from. It wouldn't work down here. We're actually planning on conducting this study again in 2024. And the idea will be to decrease the dose of both liquid Formic and Formic Pro to about half to see if that allows us to continue controlling the mites with less of an impact on the queen population. Thank you for asking that. Thank you so much, everyone.